nice to know this is being streamed, so you can reference it a little bit later. It's going to be on the STAR YouTube page, which is just youtube.ucf-STAR. You can also find my review, the materials on the UCF Study Union WordPress page. Anyway, we're just going to go ahead and get into it. Also, you can take a little survey to tell us how you think this session went. You don't gotta, but it helps us out. I'm also going to put it back up at the end. So, let's get started. Here it is. Yeah. This we're talking about this one if you were in the room, I'm sorry. So today we're going to talk about all the things that you've done in class so far. We're going to talk about vectors, kinematics, forces and Newton's laws, circular motion, work and energy, impulse, momentum, rotational kinematics, rotational dynamics, harmonic motion, and then I'll try and leave about like 15 minutes at the end for clarification and stuff. Okay, so back to the beginning with vectors. I'm sure that you all really like vectors now. They're pretty easy now. So a vector is a quantity that has both magnitude and direction. A scalar has no direction. So vectors are things like velocity, displacement, acceleration, force. Scalars are things like speed, mass, distance. Those don't have directions, right? So to keep in mind for these, you want to remember all your trig functions. Remember your SOHCAHTOA. When you add vectors, you should add them tip to tail. When in doubt, break things into x and y components. That's always a good place to start. And all you need is an angle and a side or two sides to find basically anything. So you can find any other side, you can find any other angle. So here is a practice problem that we are all going to do together. So on a safari, a team of naturalists set out towards the research station located 4.8 kilometers away in a direction 42 degrees north of east. After traveling in a straight line for 4.2 kilometers, they stop and discover they've been traveling 22 because their guide misread his compass. What are the magnitude and direction relative to due east of the displacement vector now required to bring the team to the research station? So let's see how smooth we can make this transition. Cool, that's not bad. So we have you see that? Yeah. So this is where our research station is, right? So what we have done is we have instead traveled something like this. Right? So what we want is to do something like this vector here to get to our research station, right? So let's break everything into components because that's a good way to start. So for our research station, our x component will be 4.8. Oh, sorry. Be sure to tell me if I go like off kilter. Wow, I wrote a lot of different things there that didn't need to be there. Cosine of 42. Right? Our y component works very similarly, except this will be our opposite side now. So we're going to use sine. That's not on the screen. We're going to zoom out slightly. Except this will be our opposite side this time. So for y, we will use sine. And that should give us, 3.2 kilometers. So now for what we've already traveled, we can do the same thing. So for our x, we want our adjacent side to our angle, so we use cosine again.
And that should give us 2.2 kilometers. And for our y, we're going to use sine again because this is still our opposite side. So 2.4 sine of 22. And that gives us about 0.9 kilometers. All right, so now that we have these, we know that these two vectors, the distance that we've already traveled and the distance we want to travel, will add together to give us the vector where the research station is. So we know that we can get a formula something like this, where we have the x that we've already traveled plus the x that we have to travel will equal the x of the research station. Right? So we can solve for this x. Oh, I didn't mean to cross that out. This is an underline. We want this one. So we can use our x that we've already traveled, which is our 2.2, plus the x that we want equals 3.6. So this x will have to be about 1.3. Well, it's going to be 1.4 here because I rounded more. Likewise with the y, we can do the y that we already traveled plus the y that we have to travel equals the y of the research station, which will give us a y of about 2.3. So now that we have our x and y components, we can use our Pythagorean theorem. Everyone's favorite. Because then we will have a triangle like this for this vector. So the distance that we still have to travel, which we'll call our r, and this is r, will be the square root of x squared plus y squared, which should give us about 2.8-ish kilometers. Again, I'm rounding a lot. So that's our displacement vector, right? That's how we still have to go to get to our research station. So now we want to find what direction we have to travel in relative to due east. So this direction would be east, right? So we want to find this angle. Oops, off screen. Okay. So we want to find this angle. So we can use our trig functions. Everyone's favorite trig function happens to be tangent, so we're going to use that one. So we know tan theta is equal to opposite, so that would be our y, over adjacent, which happens to be our x. So our theta will be equal to the inverse tan of y over x. And we should get about 59.8 degrees, something like that. And there we go. So we know our displacement vector will be 2.8 kilometers, 59 degrees north of east. Cool, that's our first problem done. Don't worry, there are more to come. So vectors seem kind of easy now, right? You've all done vectors for as long as you have been in physics. It's always vectors. So let's move thing a little more fun. All right, so that was our practice problem. All right, so let's talk about kinematics now, our second favorite thing. We have 5 kinematic variables: displacement, final velocity, initial velocity, acceleration, and time. We have 3 equations, arguably 4 sometimes. The fourth one that isn't up there is your x equals 1/2 v naught plus v final times time. That'll actually be in the rotational kinematics chapter as well, so don't worry about it too much. So yeah, these are your 4 equations for this. Oh no, that was the wrong way. So to solve a kinematics problem, keep in mind you want to write down, first of all, everything you have in terms of your variables. You want to separate it based on directions and cases. So by cases, I mean basically where your acceleration changes. All of these have to be used with constant acceleration, so as soon as you change an acceleration, you have like a new scenario, basically. Remember that if at your maximum height, your v final in the y direction will be 0, or where you hit your maximum height, that v final in the y will be 0. Your acceleration for x in a projectile motion problem will be 0. The final for one part of a problem could become the initial for another part. So if you go, again, straight from one scenario to another, your final velocity there might become the initial velocity in your next part. Time usually depends on the y portion of the problem. You can totally find it for x, but the gravity in the y direction is going to be the only thing that will stop you. Note your positive and negative directions. So because physics is kind of fun and arbitrary, you can put whatever you want as positive and negative. You could put left and down as positive. No one will stop you. Just remember that you put it that way. So if they ask for a direction, you know which way, if you get a positive answer, where it's pointing. And draw everything. Pictures always help. So let's do some practice problems. For this problem, we have a jetliner traveling northward is landing with a speed of 69 meters per second. Once the jet touches down, it has 750 meters of runway in which to reduce its speed to 6.1 meters per second. Compute the average acceleration, magnitude, and direction of the plane during landing. So, will this work? Yeah, probably. All right. So, for our jetliner, we know that it starts at 69 meters per second, right? We know that it has 750 meters of runway to reduce to its final speed of 6.1 meters per second. We want to know what the acceleration is. So we have v naught, v final, and x. We want a. So now all you have to do is compare it to those equations. The one that will work for this is your v final squared equals v initial squared plus 2 acceleration times x. So basically, this is just a simple case of plug in your numbers and solve it. So our v final is 6.1 squared equals our v initial of 69 squared plus 2a, and our x is 750. So we should get for an acceleration negative 3.149 meters per second squared. So what does this negative mean? Basically, we knew that all these positive values were traveling northward. So since we got a negative value, that has to be the opposite of north or south. So, pretty sweet and easy, right? Cool. Let's go. Okay. Here's another one. A tennis ball is thrown horizontally with an initial speed of 10 meters per second. If the ball travels 40 meters horizontally, how far down does the tennis ball drop? So this is a projectile motion problem. All right, so basically what we have happening here, we have a tennis ball that is hit horizontally with an initial speed of 10 meters per second. We know that it goes a horizontal distance of 40 meters. But we want to know how far it has dropped. So we want to know our y here. So since we are dealing with 2 directions, we're going to set up an x and y chart for our things. So, and we'll write all of our kinematic variables under those 2 charts for each direction. So in the x direction, we know our initial velocity is 10. Because if it hits horizontally, it only has an x component. So likewise, we also know our initial velocity in y is 0. our acceleration in x will also be 0, because that's just what it is in a projectile motion problem. Our acceleration in y will be gravity, or negative 9.8 meters per second squared. Our v final in x, because our acceleration is 0, since the acceleration is the rate of change of the velocity, if there's no rate of change, that means our velocity stays the same. We don't know what our y is. We know one more thing, and that's that we travel a horizontal distance of 40 meters. So this is everything we know. The problem we run into here is that for y, we only know 2 variables. We need 3 to solve any kinematics equation. So we're going to have to find another one. So if we think about what we could find in x that would help us in y, the one thing that isn't really dependent on what dimension you're in is time. So if we find time here, that would be our time here as well. And then that would give us 3 variables. So let's do that. So if we look at our x, if we want time, we have basically every other variable that we could possibly want. So we just got to pick one with time. So the one that will help us here will be x equals, can you see that? Initial velocity times time plus 1/2 acceleration times time squared. This may look like a horrible quadratic, but don't worry, your a is 0, so that's 0. So 40 meters is equal to 10 meters per second times t. So your t will be 4 seconds. So we can bring that up into here. We have enough information to solve for y. So for y, we have v naught a t, and we want y. So we can use the same equation here. So this will give us y equals v naught t plus 1/2 at squared. Again, quadratic. This one will now go away because your initial velocity in y is 0. So your y will be equal to 1/2 negative 9.8 times 4 squared, which will give you negative 78.4. So the ball dropped 78.4 meters. Now it's negative because you go below your origin, right? So if you end up with a negative displacement, that means that you've gone down. Your displacement vector points downward. Cool? Yeah, so that's that. Back to the computer. This is all coming back to you guys a little bit, doing all these projectile motion problems. Yeah. All right. Let's move on to forces and Newton's laws. Here are Newton's laws heavily abridged. So for our first law, an object continues in a state of rest or a state of motion at a constant speed along a straight line unless compelled to change state by a net force. Basically, an object doesn't want to change without a force. It'll just stay the same forever until you apply a force to it. Second law, net external force acts on an object, the acceleration that results, whatever. This is F equals ma. You can write any force as F equals ma as well. If that's the one thing you take from this, that should be it. You can write any force as F equals ma. Normal force, frictional force, centripetal force, any type of force. Third law, whenever one body exerts a force on a second body, the second body exerts equal and oppositely directed force of equal magnitude on the first body, equal and opposite reactions. If you have a fly hit a truck, the truck exerts the same force on the fly as the fly exerts on the truck. All right, so some tips for solving these. You want to draw a free body diagram. It always helps. Pictures always help. Always draw things. Draw things forever. Write down literally everything. Even if you're not entirely sure if it's important, it's probably important. When you're in equilibrium, you have no acceleration, so the sum of all of your forces is 0. Use that to your advantage. Mass isn't always important, so if you end up not having a mass and looking at something and going, well, I think I need a mass to solve this. You might not. It might just cancel in the end. Normal force is always perpendicular to the surface, and it is not always equal to mg. Do not fall into that trap. If you have no other vertical forces except for normal force and mg, it will be equal to mg, but not always. Friction force is opposite to motion, so your friction force will always oppose the direction that you're going to try and go into. Tension will be along a rope, and it will always point away from the object where you're measuring the force. So if you have a box hanging on a rope, your tension will point away from the box. And gravitational force is always straight down. It always wants to point towards the Earth, and the Earth is generally straight down. All right, wow, who could have guessed? More practice problems. So here we have a 912 kilogram car is being driven down a straight level road at a constant speed of 31.5 meters per second. When a driver sees a police cruiser ahead, she removes her foot from the accelerator. After 8 seconds, the speed of the car is 24.6 meters per second, which is the posted speed limit. What is the magnitude of the average net force acting on the car during this 8-second interval? All right, so new paper. Let's start by writing down everything. So we know the mass of the car, which is 912 kilograms. We know the velocity that she starts at, which is 31.5 meters per second. We know that it takes her 8 seconds to decelerate to a final velocity of 24.6 meters per second. So we want to find the force that acts on this car during this 8-second interval. So since we know that force is equal to mass times acceleration, we have a mass. We need an acceleration though. So, but if you look at V naught, V final, and T, that looks like kinematics. So we can use that. That we know if we want acceleration, we have V initial, time, and V final. We can use our equation, not that one. V final is equal to V initial plus acceleration times time. Alternately, if you remember this equation, that is the same thing. So if you plug in all of your values for these, you should get that your acceleration is negative 0.8625 meters per second squared, which basically just means she's slowing down. So then to get our force, force is equal to mass times acceleration, which will be equal to our mass of 912 times our acceleration of negative 0.86 whatever. So for our force, we get negative 786.6 newtons. So the magnitude of our force is 786.6 newtons. Cool? If someone asks you for the magnitude, you do not put a negative sign. They just want to know the value. Because like I said, you can kind of define whatever you want as positive and negative, and no one can really tell you otherwise. Unless the problem says this is in the positive direction, then keep that in mind. But if it doesn't, then you can just define whatever you want. Cool, pretty straightforward, right? All right, so another problem. A child decides to go sledding on a snowy day. The child is initially moving at 4.9 meters per second, but eventually slows to a stop. Assuming the coefficient of kinetic friction is equal to 0.1 and the child's weight is 50 kilograms, what is the friction force and what is the child's acceleration? So, back we go. All right. So we have a child sledding. This is our sled and our child. So we know initially he's going with 4.9 meters per second of velocity. But friction force brings him to a halt. Right? So we know about this. We know the mass of our child is 50 kilograms. We know our coefficient of kinetic friction is 0.1. We know our initial velocity is 4.9 meters per second. We know our final velocity is 0. So what we want to know is our friction force and our acceleration. So even if you were to look at this in reference to kinematics, you don't really have enough information to solve straight out for acceleration, right? So that's probably not something that will work here. What we can do instead is, hey, let's draw a free body diagram. So if this is our child in our sled, we know that he has weight pointing downward. We know he has normal force from the ground. And since he's moving this way, our friction force has to point the opposite way. So we can use, first of all, our frictional force equation, which is friction force is equal to the coefficient of friction times normal force. Right? So we have our coefficient. We don't have normal force. So let's look in our y direction to find normal force. So we know in the y direction, we're not moving. We're in equilibrium because he's not going to leave the ground. So the sum of our forces in y is 0. The forces we have acting in y are normal force, which points upward, so we'll say that's positive, and our weight, which points downward, so we'll say that's negative. So if we solve that for normal force equals mg. So we can take this and plug it into this equation. So that will give us our mu k mg. And since we know our mass is 50 kilograms, we know this is 0.1, and we know our gravitational force is always 9.8. We can go ahead and solve this. So this is 0.1, 50, 9.8. And that should give us 49 newtons of frictional force. So now that we have this frictional force, we can find our acceleration, right? Because any force can be written as ma. So we know our frictional force as well is mass times acceleration. So we can set our 49 newtons equal to 50 kilograms times A. So our acceleration will be 0.98 meters per second squared. And there we go. Right, again, not super bad, right? So let's go back to the computer. Also, if you miss anything that I write down, also these will be posted to the Study Union WordPress right after this. I will post them before I leave this room. All right, here's another practice problem. A worker stands still on a roof sloped at an angle of 30 above the horizontal. He is prevented from slipping by a static friction force of 390 newtons. We want to find the mass of the worker. Also, if any of these seem familiar, it's because they're all from the book. So, let's go and talk about this one. So, let's go down here. This is our worker. So he's held in place by a static friction force, right? So if he's held in place and is stopped from sliding down that roof, so if he wants to move this way, that means our friction force has to go this way. Right? So let's actually So if this is our guy, he has a frictional force going this way. Since he's standing on a roof, he'll have a normal force perpendicular to that roof. And he will also have a weight downward. So we want to find his mass. We want to find m. So it's kind of hard to do that here, to do it with looking at it this way. So what we're going to do instead is we're going to flip our axes. So basically what happens when we do is that along our normal force, this is our new y-axis. And along our ramp is our new x-axis. So then only one thing is actually going off at an angle, and that would be our mg. So what happens to mg is that, if I can draw a quick close-up, because I didn't really leave myself enough room for that. So for mg, where this 36 was here, the 36 now comes in between our new y-axis and our mg. Cool? Geometry. So, with that in there, that'll give us two components for our mg, right? Now we have a y and an x. So, back to talking about our worker. Since he stands still on our roof, he's not moving. That means he's in equilibrium. So the sum of all of our forces will have to be 0 in both our x and our y direction. So let's look in the x direction, because we know more stuff about that, right? We know our frictional force, which goes in our new x direction. Which will equal points this way. Anything that points that way will be negative. So if we plug in here, we get negative, what was our frictional force? 390. Right? $36. And this all equals 0. So we want to figure out what m is. We know what g is. It's always 9.8. So we can solve for our m. All right. So yeah, forces, not too bad, right? Physics kind of builds on itself, so you probably worked with forces a lot more now. You probably feel a lot better than when you started, right? So let's talk about circular motion. So basically, if you have something moving in a circle, it will have a constant speed but a changing velocity. So that's because your velocity vectors will constantly change direction. And since they're changing directions, they're not the same velocity vector. But your speed, which is just velocity without a direction, just will stay the same. So centripetal acceleration will point towards the center of your circle. Basically, it's the thing that will keep you inside of the circle. So like if you had an airplane that you were spinning around on a rope, the tension along that rope will be the thing that keeps you in that circle. Cool? Here are some helpful ones. V equals R over T is commonly used for circular orbits. Basically just anything traveling in a circle. V equals the square root of g m over r. This is also used for circular orbits. Your g is your gravitational constant. I don't know why that ended up as 10 minus 11. It was 10 to the negative 11th. But you also want to be careful when using this as well, because your capital M is the thing you are orbiting around. So it's not the mass of the thing that is orbiting, it's the thing that is being orbited. Cool? Centripetal acceleration equals v squared over r. Centripetal force is equal to m times centripetal acceleration. This is also the one with those fun banked and unbanked curves. So basically, centripetal force is not another force. It's not like a thing on its own, right? It's always kind of takes the place of something else. So centripetal, you won't have like, oh, I have this and centripetal force when they're both pointing inward towards the circle. It's just this thing is equal to centripetal force. Does that make sense? So for unbanked curves, static friction force is the centripetal force. For banked curves, it's the horizontal component of the normal force. And I'm pretty sure I have one of those questions in here, so you will see what I mean if you don't know. All right, here's our first practice problem for that. A swing ride at a carnival consists of chairs that are swung in a circle by 15-meter cables attached to a vertical rotating pole, as the drawing shows. Suppose the total mass of the chair and its occupant is 179 kilograms. What is the tension of the cable attached to the chair, and what is the speed of the chair? All right, so talk about that. So we have the mass of our rider and our chair is 179 kilograms. And we want to know velocity. Cool? So, if this is our rider here, so but he also has tension. And in our drawing also. So, if this is our y, and this is our x, we know that in our y direction, if he stays in that same circle that he's traveling around, so like this is kind of the circle that he's going in here, right? So if he stays in that circle, then the sum of he's not going to move in his y direction, right? So the sum of the forces in his y direction are 0. However, the sum of the forces in his x direction are not, because there's something that's keeping him in that circle. And the only thing that's acting directly in that circle will be the x component of tension. So the x component of tension has to be our centripetal force. So we know the sum of the forces in x will which is also equal to m v squared over which is also equal to the x component of tension. for the opposite side. So let's revisit this idea. So the sum of our forces in y are 0. If we're going to say up is positive, that'll give us Ty minus mg, which equals 0. Vt cosine of solve this for t, we should get t is
9.6 newtons. Pretty big, right?
so that actually gives us the answer to our first part of our problem.
Where's our tension? Now we want to find out what our velocity is. So now let's revisit
This equation. So we know mv squared over r is equal to t sine of 60. Now r is not L. Does that make sense? So like if you have, this is your L, right? This is your swing. You're going in a circle around this portion of it. So the radius of the circle is this part. Sine of 60. So now we can go into this equation and plug stuff in. So our m we know is 179. We're looking for our v squared. Our r is 15 sine 60. Our t was that 3,449.6 times sine of 60. So if you solve for your v, you should get that v is 14.7 meters per second. Cool. Let's keep going. Another problem. Curves on roads in such a manner that a car going around a curve at the recommended speed does not have to rely on friction between its tires and the road surface in order to round the curve. Suppose the curvature of a given curve is 60 meters and the recommended speed is 40 kilometers an hour. At what angle should the curve be bent? Here's one of those curve problems. All right.
We know our radius of curvature, so our arc, 60 meters. We know the velocity that we're going to round this curve with is 40 kilometers an hour.
Those are not super good units. So the first thing we're going to do is convert kilometers per hour to meters per second. So we know if we want to get rid of kilometers, we know there's 1,000 meters in 1 kilometer. We know in 1 hour there's 60 minutes, and in 1 minute,
60 seconds. So your kilometers will cancel, hours cancel with hours, and minutes cancel with minutes, which will give you meters per second. So that should give you
11.11 meters per second. All right, so we have a banked curve. So that basically means it's going to look something like this, where this is your car.
We're going around in a circle like this. This distance here is your radius. So what forces do you have acting on you? Well, it said that we don't want to depend on friction.
So no friction. We will always have weight downward. And then we have normal force going perpendicular. Right? I'm going to move this a little bit.
So we want to find the angle theta at which we should make this curve. So basically, we're going to want to find a centripetal force. Right? So like I said before, for our banked curves, the centripetal force is the horizontal component of the normal force. I know before in our rep problems we were tilting axes, but it doesn't really work with this because then that would give our centripetal force some weird components and we don't really want that.
So we're
We're going to leave it like that. So the horizontal component of the normal force, basically to find that, your angle, theta, will come up in here. This is theta here, between your y-axis and like where your normal force points. You do that because it's perfectly function. So we know that our centripetal force here
which is mv squared over r.
will be equal to the horizontal component of our normal force, nx. Or, since this will also be nx, n sine of theta. It's our opposite side, right? Probably should put this n up here. This will be nx and ny. So this will be n times sine of theta. So, in order to solve for our theta, we have our radius. We don't have a velocity. Wait, do we? Yeah, we do. We have a velocity, I'm sorry. We have a velocity, we have our radius. We don't have a mass, but remember what I said about mass might not always be important? So let's not worry about that for now. We will, however, need an n. So to get our n, let's look in another direction. Let's look at our y direction here. So if we stay in the same circle around this whole way, we shouldn't actually move up or down in our ramp or like this way. Does that make sense? Because we want to keep the same radius. So we can't move up or down. So the sum of our forces in y will be 0. Because we're not going to move. So in the y direction, we have ny, which will point upward, so that will be positive, and mg, which will point downward, so that will be negative. And y can also be written as n cosine theta. So we know n will be equal to, since this is all equal to 0, n will be equal to mg divided by cosine theta. Right?
Cool, maybe.
So now let's take this n and plug it in here. So I'm going to move this down a little bit. So that will give us mg squared over r is equal to, instead of n, mg over cosine theta, sine theta. So since every term has an m attached to it, they'll just cancel. radius was 60. We know G always 9.8. You can just take the tan inverse of that, and you should get that your theta should be 11.8 degrees.
Yeah.
All right, let's keep going.
We're actually right on schedule, which is like this is the first time that's ever happened to me. So, practice problem 9. So we have scientists determine the masses of planets by observing the effect of the gravitational field of those planets on nearby objects, mainly upon their moons. By measuring the orbital period and orbital radius of a moon about a planet, Newton's laws of motion can be used to determine the mass of the planet. Phobos, a moon of the planet Mars, was discovered in 1877. Its orbital radius is 9,380 kilometers, and its orbital period is 0.319 days, which is 2.77 times 10 to the 4th seconds. Determine the mass of Mars based on this data. Let's.
All right. So the fact that the moon was discovered in 1877 is not important. That's something you don't have to write down. So, what we do know, our orbital radius is 9,380 kilometers. Which, if we want that in meters, is 9,380 times 10 to the 3rd meters. We know our orbital period, our capital T, is 2.77 times 10 to the 4th seconds. So we want to know the mass of Mars.
So, two equations.
That can help us out with this are B equals 2 pi r over T, and B equals the square root of gm over r. Right, because that's the only thing that this is the only one that will give us anything based on what we're orbiting around, and we want to know the mass of the thing we're orbiting around. So that's kind of a hint to use this one. Our time period also, this is the only one that we really know that uses our time period in this chapter, so we're also going to use that. So we can set these two equal to each other, right? Because they're both equal to the same orbital velocity. So since we want to know the mass
of Mars.
we have that 2 pi r over T is equal to the square root of capital G m over r.
Right?
So, since we know r, we know T, we know r, G is our gravitational constant. 6.673 times 10 to the negative 11.
Then we actually have everything we need in order to solve for m.
And if we actually do this out, you get 2 pi squared r squared over T squared is equal to gm Mars over r. So then if we solve this for m, we'll get 2 pi squared r cubed T squared over T. So the mass of Mars should be equal to 6.36 times 10 to the 23rd
Grams. Oh yeah, I was going off the thing, sorry. So I mean, and that's a good way to check yourself, is planets are pretty big. So you shouldn't get like 5 kilograms, that would be a very small planet. But yeah, so cool on this one? Yeah, let's keep going. All right, let's talk about work and energy. So we know our work is equal to force times distance times cosine theta, which is basically your force and distance that are parallel to each other. You guys might remember now that you have your torque, which is also force times distance, but those are perpendicular. That's why you don't measure torque in joules. Cool? So work can also be measured as change of energy of a system, where you have potential energy due to gravity, which is your mgh, and kinetic energy, which is 1/2 mv squared. And we'll get into the other two types of energy you know as well a little bit later. So energy will be conserved if the system is only acted on by conservative forces. So basically, you have 3 conservative forces. There's really only 2 that you have to worry about, and those 2 are gravity and elastic spring force. Electric force will happen in physics too, which I'm sure you're all looking forward to. So basically, a non-conservative force is anything that is not those 3, which is like the easiest way to describe it. So basically, just anything that is not gravity and elastic spring force. So for example, static friction, air resistance, tension, normal force, propulsion of the rocket, which is a specific one people really like to give when give examples of these. So and you also have your 2 to non-conservatives is equal to change in kinetic, change in potential. So, and it will be 0 if you only have conservative forces, right? Here's more practice problems. So we have a motorcyclist is trying to leap across a canyon by driving horizontally off a 70-meter high cliff at 38 meters per second to hit the 35-meter high cliff on the other side. Ignoring air resistance, find the speed with which the cycle strikes the ground on the other side. So, let me get a new paper. So what's happening here is we have a motorcyclist who drives horizontally off the cliff at 38 meters per second. And this cliff is 70 meters high. He does this to hit another cliff, which is 35 meters high. And his final velocity should probably look something like that. We want to know what that final velocity is. So after he drives off the cliff, the only force acting on him is gravity. So since that's a conservative force, his work due to non-conservatives is 0. Cool? So we know work due to non-conservatives is equal to 0. Which is also equal to change in kinetic plus change in potential. So we know 0 will equal 1/2 m the final squared minus 1/2 m the initial squared plus mgh final minus mgh initial. So if we start to fill these out, we know our initial velocity, which is 38 meters per second. We know our final initial height. So actually, it's down here. 0 is equal to 1/2. And actually, no, before I do that, this has an m, this has an m, this has an m, this has an m. 0 divided by m is still 0. So we can get rid of all those, right? Math doesn't matter. It's a crazy thing that happens a lot of these problems. So, our final velocity is what we're looking for. Our initial velocity is 38 plus our height final is 35 minus our height initial, which is 70. So basically, if you solve this out, you should end up with a final velocity of 46.1 meters per second. Pretty straightforward, right? Fun fact about this problem, you can also solve this using kinematics, but I will leave that to you guys to do. But it's totally doable. So, That was the only problem I had for that one, so let's continue. And momentum. So impulse is net external force times the time force x, right? So basically, this F is an external force, something that happens outside of your system. The fun thing is you can define what your system is. So a lot of times your net external force is 0 because you just define your system as everything that's happening. So your linear momentum is mass velocity, P equals mv. Impulse is your change in linear momentum. So J equals change in P. So like I said before, if you have no external forces, J equals 0. So your momentum initial and your momentum final will be the same thing. Cool? So basically you have three major types of collisions. You have elastic collisions where objects bounce off each other. So for these, your kinetic energy and linear momentum will be conserved. You have basically inelastic and perfectly inelastic are kind of like, they're very similar. So the basic thing for those two is that your linear momentum will be conserved, but not kinetic energy. Kinetic energy will not be conserved for those. So elastic kinetic energy is conserved, inelastic it is not conserved. Linear momentum, always conserved. Cool? Unless you have external forces, but this is when there's none of those things. All right, more practice. Starting from rest, two skaters push off each other on ice where friction is negligible. One is a 54-kilogram woman and one is an 88-kilogram man. The woman moves away with a speed of positive 2.5 meters per second. Find the recoil velocity of the man. So, that's not what I wanted to do. This one. So now we have to So when they start, they're holding on to each other and not moving. So their initial velocity is 0. But then they push off of each other. Right? So after that, they're both going to collide. You will also know the problem, if I can do it real quick. Just kidding, nothing is quick about this. You'll notice in the problem that it says that she moves away with a speed of positive 2.5 meters per second. That means they have decided the direction for you. So whatever way you decide the woman goes is your positive direction. Does that make sense? So let's go back. Probably. All right, so we know the mass of our woman, which we'll say is mass 1, is 54 kilograms. We know the mass of our man, which we'll say is mass 2, is 88 kilograms. And we also know V1 is positive 2.5 meters per second. So since this is how we drew our picture, we drew our V1 going to the right. That means that we'll say this direction is positive. Cool? So, since we have no net external forces, again, we're going to say that all of our forces are internal to our system. We're going to say that our change in momentum is equal to 0. So, our P final is equal to our P initial. And we also want V2. That's what we're looking for. So for our P initially they're holding on to each other. So they're kind of acting like one object, right? So we sum their masses times their initial velocity. However, initial velocity here is 0. So this whole thing will equal 0. Now for P final, we know that they both go their separate ways, so now they're separate objects. So this will give us M1 V1 plus m2 v2. So we know all the stuff for this one, we know the mass for this one, and we want to find v2. So we can set P initial equal to P final because our energy is conserved. So that will give us 0 is equal to our mass 1, 54, times our velocity 1 of 2.5, plus our mass 2 of 88, times V2, which we're trying to find. So when you solve this out, you should get V2 is equal to negative 1.53 meters per second. Which basically means he's going away from the woman. Cool? Yeah, not bad, right? Momentum was a pretty good chapter. So, rotational kinematics works exactly the same way as linear kinematics. So basically, the only thing that changes is that your variables now become thetas, alphas, omegas, and t, of course, stays the same. Because time doesn't care. So you have your angular displacement theta, angular acceleration alpha, final angular velocity omega, initial angular velocity omega naught, elapsed time is t, and then there's all those equations. As you will notice, they look very similar to your linear ones, right? Except now you've just replaced your displacement, accelerations, all those, with their angular versions. So, same thing. And this also was one of the equations that I told you about too. Again, some professors give it, some do not, so. We have our bridge equations. So we can get our tangential acceleration, or our linear acceleration is another way to say that, which is radius times alpha, v tangential, or v linear is r times omega. Your s is your arc length of your circle, which is r times theta. The thing to remember when using these two is that your alpha, omega, and theta are all going to have to be in radians, right? So if you have omega in like revolutions per second and you want to use one of these, you have to convert it to radians first. Cool? Here's more problems.
The wheels of a bicycle have an angular velocity of 20 radians per second. Then the brakes are applied. In coming to rest, each wheel makes an angular displacement of 15.92 revolutions. How much time does it take for the bike to come to rest? What is the angular acceleration in radians per second squared of the wheels? So,
we know that initially our wheels are traveling at 20 radians per second. Then we have our brakes are applied, and we know that they're going to come to rest. So that means our omega final will be 0. We know that they come through an angular displacement, so a theta of 15.92 revolutions. That does not match our other stuff.
So we're going to convert this to radians. So in one revolution, there are 2 pi radians. So this gives us
100.03 radians. So we want to know, first of all, how much time it takes
us to come to rest. And then we want to know what our angular acceleration is. So let's
with time. So again, with kinematics, we wrote down everything that we had. We have omega initial, omega final, and theta, and we want t. So the equation that works best for this one is theta equals 1/2 omega initial plus omega final T.
So that gives us 100.03 radians equals 1/2 omega initial of 20 plus omega final, which is 0.
It's T.
This will give us that our T is about 10 seconds. So that's the first
Part of our question done. Next, we want to find alpha, or our angular acceleration. So along the same line, now we have all of these variables, right? Because now we know our t is also 10 seconds. So you can kind of pick your favorite equation with alpha.
The one that I used was
Omega squared is equal, omega final squared is equal to omega initial squared plus 2 alpha theta.
So again, all you gotta do is plug everything in. Omega final is 0. Omega initial is 20 squared plus 2 alpha, or theta is 100.3. So alpha should come out to negative 2 radians per second squared.
Cool. So again, these work just like kinematics, right? We did basically the same steps. Talk about torque, which is, I'm sure, everyone's favorite chapter, like ever, right? So rotational dynamics, another name for torque. Most problems deal with relating the two equations for torque together, where you have torque is equal to I alpha, and also equal to the sum of your forces times your lever arm times sine phi. So this is the force times lever arm times sine phi basically says that your force and your lever arm have to be perpendicular to each other. Cool? So you can use sine phi. Phi is measured from the lever arm to the direction of force. So basically to measure phi, I'll actually draw a picture of it when we start doing a problem. To measure phi, you have to extend your lever arm and take the angle between your extended lever arm and your force. So, cool. Sometimes it involves fancy trig, and no one really likes that. So pick your battles. The maximum torque will be when phi is equal to 90, or when sine phi equals 1. So basically, when you have something that's already perpendicular to your lever arm, that is applying the maximum torque. So it's kind of like how if you push on a door towards the hinge, the door's not opening, right? But then if you push on the door perpendicularly for the hinge, that gives you the maximum torque that you can have. Cool? So we have rotational kinetic energy, which is just another type of kinetic energy, which is 1/2 I omega squared. Omega must be in radians per second. Basically, when in doubt, just change everything to radians. And angular momentum is L equals I omega. So basically, that kind of works exactly like your linear momentum, where if there's no net external torques, it's conserved. And torque is the rate of change of angular momentum. Fun fact. So basically, if something is in equilibrium, your acceleration is 0, the sum of your forces is 0, your alpha is 0, and the sum of your torques is 0. So basically, everything's 0 forever. In general, I equals the sum of mr squared for the whole system. So basically, if you just have like random points rotating about an axis, then your inertia will be mr squared, and the sum of all of those. If you have like a bicycle wheel rolling down a hill, they'll give you the formula for inertia. You don't gotta remember those. They give you like some weird ones, like frozen cans of juice and like stuff like that. It's weird. But they'll give you equations for those. All right, here's some practice problems.
we have a hiker.
Who weighs 985 newtons, is strolling through the woods and crosses a small horizontal bridge. The bridge's uniform weighs 3,610 newtons and rests on 2 concrete supports, one on each end. He stops 1/5 of the way along the bridge. What is the magnitude of the force that a concrete support exerts on the bridge at the near end and the far end?
All right. So kind of what we have going on here. This is our bridge. We have 2 concrete supports. One over here, which we'll call the far end. And one over here, which we will call the near end. So we know the weight of our bridge will happen in the middle. Okay? That's where that force will occur. So this is our weight of our bridge. We have a hiker who walks 1/5 of the way out of the bridge. So this will be our hiker. This is 1/5 of the length of the bridge. The whole bridge is L. And he also has a weight. Okay? So we want to find force from the near side and the force from the far side.
So this bridge will probably not tip. I mean, we can make that assumption. That would be a really scary bridge.
So we're going to say that this bridge is in equilibrium. So if this bridge is in equilibrium, the sum of our forces is 0.
And the sum of our torques is also 0.
So if we were to try summing forces immediately, we'd end up with 2 unknowns. We don't know this Fn, we don't know Ff. We know these 2, but I mean, it doesn't really help us that much, right? So
Instead, we're going to sum torques. So the very first thing that you want to do when you start a
torque problem is you want to pick a pivot point. So basically, you're saying that if our system was to tip, it would tip around this
point.
point.
So
Arbitrarily, we are going to pick our pivot point at force far.
cool. Then we're going to pick a positive and negative direction. So
We're going to say arbitrarily, our positive direction goes this way. I know counterclockwise is generally positive, but
again, you can kind of pick whatever you want,
as long as you know
what it means.
So this will be our positive direction. Anything that helps us tip this way will be positive. Anything that stops us from tipping that way will be negative.
So we know the sum of our torques is 0. And so now we're going to go down the line and decide what all these things give us.
So we know our torque is equal to force times lever arm perpendicular to each other. Right? These are all already perpendicular, which is super great. So for the weight of the bridge, in order to find out if this is a positive or negative force, you can hold your pen at the pivot point. That's too far out. You can hold your pen at the pivot point and point your pen along the direction of your lever arm, and then apply the force. So the weight of the bridge goes down, right? So if you apply a downward force, that's not helping us spin this way. So this will be a negative force. Cool? So we will have
Negative weight of the bridge times its lever arm.
So the lever arm is from our pivot point out here. So since this is the weight of the bridge has to happen in the middle of the bridge, right? So that will be half of L. Now if we move on to the weight of the hiker, this will again be a negative value, so it will not help us spin this way. So that will be minus WH. Now its lever arm, we know that this is 1/5 of L, this distance here. So since we want from here to here, that has to be 4/5 of L. last force is force near. So this will help us spin in the direction we decide is positive. So that will be positive. And then its lever arm, it is the whole distance L away from our bridge. So now we can solve for Fn. So since everything has L's attached to it, and again 0 divided by L is still 0, we can get rid of all the L's.
So now we can just start plugging stuff in. So the weight of our hiker, or I'm sorry, the weight of our bridge was 3610 times 1/2 minus the weight of our hiker, which was 985 times 4/5 plus Fn, because L there just is a 1.
And that all equals 0. So if you solve for Fn,
You get 2,593 newtons.
now when it comes to solving for force phi, there's actually 2 ways we can do it. We're going to do both ways.
So
For the first way, which is a little bit harder, but again, good practice, we can take our bridge down, and since we found this force here, we could redefine our pivot point somewhere else, so we can use this force in another torque equation, right? So let's redraw the bridge real quick. So instead of defining our pivot point here, where we can't get this force, let's instead define it over here. So this will be our new pivot point. So this time I'm going to say this way is positive. Again, kind of arbitrarily. So this is force near, this is the weight of the hiker, this is the weight of the bridge, that's force moment. So if we sum our torques again, this will give us, if we go out this way this time, this will give us negative weight of the hiker times the lever arm. So this
distance is still 1/5 of L, right? From here to here?
So 1/5 L. Next is the weight of the bridge, which will also be negative. This lever arm is still L over 2.
Because it's still half the distance. And then force phi, which will in this case be a positive force because that will help us. And our lever arm there is L. So again, we can cancel our L's.
Which will leave us with 0 equals negative weight of the hiker, which was 985 times 1/5 minus the weight of the bridge, 3,610 times 1/2 plus F bar.
So if you solve this, F phi should be 2,002 newtons. Now there is a slightly easier way to do it. And that way is, since we know that we're at equilibrium, not only our torques will sum to 0, but also our forces. So that's the thing that we talked about in the beginning of this problem, right? We couldn't do it in the beginning because we didn't know all of our forces, or we had 2 unknowns. Since we solve for Fn, that would replace one of our unknowns, right? Then we would just have 1. So let's also do this with sum of forces, acting like we know this but do not know FF. Yeah.
So if we summed our
Forces. They would sum to 0. The forces we have acting are our two positive forces are Fn and Ff.
So Fn plus Ff.
Negative forces are the weight of the bridge and the weight of the hiker, because those point downward.
So, putting these back in, we know the force near is 2,593 newtons plus force far minus the weight of the hiker minus the weight of the bridge. So when you solve for this, for force far, you will also get 2,000.
And there you go. Two different ways to do it. The force one is arguably easier. So as soon as you can get it down to just one unknown, I would suggest probably using this method, but whatever floats your boat. Again, it's good practice to check yourself too, so even if you have one that you can do it and you're like, maybe I should check and make sure, you can do that as well, if you have time. I mean, you guys are gonna have a 3-hour exam. So, let's continue. One more. We have a bowling ball encounters a 0.76
meter vertical rise on the way back up the ball ramp, as the drawing illustrates. Ignore
frictional losses and assume the mass of the ball is distributed uniformly. The translational speed of the ball is 3.5 meters per second at the bottom of the rise. Find the translational
speed at the top.
So, basically, by saying ignore frictional losses, they're trying to tell us that our energy will be conserved. So when our energy is conserved, our work due to non-conserved
Forces is 0, right?
So,
We know our work due to non-conservatives is going to just be 0, right? Now there's two other
things that are going to be important for this problem. The first one is the inertia of a sphere, which is, again, not a thing you gotta know off the top of your head.
head. So the inertia for a sphere, in this case our bowling ball, would be 2 bits.
mr squared. Another important thing to keep in mind for this problem are those bridge equations we talked about back in rotational motion or centrifugal acceleration, right? No, that was rotational dynamics or whatever. Rotational kinematics. Wow, that was a lot of words to take me to the right one. So remember those bridge equations that we did where we had like V equals R omega? That will be important here. So we're going to say that omega is equal to V over R, or V equals R omega. Those will be important.
So, since we have that our work due to non-conservatives is 0, we can do out that long equation on just one side of the thing. Let's change your kinetic plus change your potential. I'm instead going to separate it into energy
Initial and energy final are equal, because that makes it a little bit clearer sometimes. So we will put energy initial equals energy final. So for our energy initial, we have 1/2 mv initial squared plus 1/2 I omega initial squared plus mg h initial for energy.
final. They have basically the same thing, just all the final versions.
Cool. So
Basically, we know that at all times the ball is going to be
rolling and have some kind of speed, right? So we
We knew that at the bottom of the rise, so our initial situation, our speed was 3 meters per second. And we also went up a height of
0.76 meters. So this will actually be a height final because we started on the ground and went up. So since we started on the ground, we started at h equals 0, right? So this goes away because our h initial is just 0. So let's start filling out stuff we know. We want to find v final. This is our ultimate goal. So we know 1/2 m v initial is 3.5 squared plus 1/2 our I is 2/5 m r squared omega naught squared. And this will equal 1/2 m v final squared plus 1/2 2/5 m r squared omega final squared plus mg h final, which is 0.76. We got all these omegas. Not good. But, oh, actually that's a little bit weird, isn't it? But we do know omega is equal to v over r, right? So let's replace all of our omegas with those. But actually, before we go any further, we have m, they can all cancel. So this will give us, did I write down actually a value I got for that? No. Why would I? Plus, and this will give us 2/10
r squared e over r, just the initial over r squared equals 1/2 e final squared plus over 2/10 r squared e final over r squared or r quantity squared plus g. Makes sense.
Since this is v initial, this is our 3.5, right? We can actually combine these two. This will just be a number. Because if we have this whole quantity squared, this is 1 over r squared down here. So that r squared and this r squared will just cancel. Same thing over here, r squared and r squared go away. That is really far up. So this will give us 1/2 3.5 squared plus, instead of 2/10, we'll reduce that to 1/5 3.5 squared, and that will equal 1/2
v final squared plus 1/5 v final squared plus g 0.76.
So this, if you solve this out, should reduce to about 1.127 equals 7/10 v final squared. So that should give you a v final of 1.3 meters per second. This one's just a lot of math. And a lot of cancellation too. So like I said, there's a lot of things that you don't really have to worry about. Like mass just totally went away. Radius, whatever, no one needed it. So, but it's also kind of mind-blowing that if you ignore frictional losses, you could have a bowling ball the size of Texas and it doesn't matter. You
It can weigh 7,000 pounds or it can weigh 0.1 pound. And it doesn't matter. Crazy, right? Anyway, we'll keep going. You obviously
Fine, this is interesting.
I may be biased.
Let's keep going.
So now we have two discs
Rotate
rotating
about the same axis. Disk A has a moment of inertia of 3.4 kilogram meters squared and an angular velocity of 7.2 radians per second,
Disc B is
rotating with an
angular velocity of
negative 9.8 radians. The two disks are linked together
together then without the aid of any extra
torques, so they rotate as a single unit with an angular velocity of negative 2.4 radians per second. The axis
axis of rotation for this unit is the
same as that for the separate disks. What is the moment of inertia of disk B?
So, this looks like a conservation of momentum problem, right? We have no net
External torques, so that means our angular momentum is conserved.
So we know the moment of inertia for this.
Okay. Which will be 3.4 kilogram meters squared. We know disk A's initial velocity, which is 7.2 radians per second. We know the initial velocity for disk B, which is negative 9.8 radians per second. And we know the velocity when they're joined is negative 2.4 radians per second. We want to know what the inertia of B is.
So, since we know this is without the aid of any external
Torques.
our angular momentum is conserved. So, our angular momentum initial, we ignore angular momentum. So kind of what's happening here is we have, let's say this is disk A, and it's rotating.
With some omega A. And then we have disk B, which is rotating with some omega B. Well, actually, it would be going the other way, wouldn't it? Yeah, because it's negative. So then we put them both
Together. And they rotate together. Right? So this is our initial. That's perfect. So for our initial, we have two separate disks. So they're acting individually. So we sum them separately. So we have the inertia of A times its velocity plus the inertia of B times its angular velocity.
for L final.
They're rotating together. So they're going to act kind of like one object. So we can sum their inertias.
Times their final velocities. Cool? So we can set these two equal to each other.
So that will give us IA omega A plus IB omega B equals IA plus IB omega AB.
And we want to solve for IB. Right?
So to do that, we're going to distribute out this omega AB to both. And then we're going to combine our IBs on one side and everything else on the other.
So this will give us IA omega A minus IA omega AB, which is equal to IB omega AB minus omega B. So if we divide this, we'll get our IB, and our IB should end up being 4.41 kilogram meters squared when you plug in all your values. All right, just got one more thing to go. All right, let's talk a little bit about harmonic motion before we end. So K is known as the spring constant, which is basically how stiff your spring is. He probably has a very low spring constant, like an industrial grade spring, or like there's springs on your car. I don't remember what they're called, but those probably have a much higher spring constant, right? So your force applied is equal to Kx. So basically, that's how much force you apply to stretch or compress your spring. The restoring force of a spring is Hooke's law, and that's negative Kx. So basically, that's the force that the spring will apply to try and get back to its equilibrium state. It's just going to be equal and opposite to the force that you apply. So here's some fun equations. I know sometimes professors will not give you sine omega t, all those. So basically, if you want the maximum displacement or velocity or acceleration, you leave off all those sines and cosines. Cool? So your displacement will be a cosine omega t, velocity will be negative omega sine omega t. All those. You guys can read, I won't read them to you. But the thing, yeah, so basically A is your amplitude, which is, again, your maximum displacement. So that's as far out as you will stretch or compress, all those. Omega is your angular speed, so that is exactly the omega that you were using before, which is also your oscillations, and that is equal to the square root of your spring constant over the mass of your thing. Maximum displacement, velocity, acceleration happen when your cosine and sine are equal to 1. So you'll also note that your velocity will not be at a maximum when your acceleration is at a maximum, right? In fact, your velocity will be 0 where your acceleration is max, right? And likewise with your displacement, that if your velocity is at maximum, your displacement will be at its absolute minimum, which is 0. People who may have taken calculus before will recognize these are all derivatives of each other. If you haven't taken calculus, don't worry about it. All right, some more helpful equations. T is the time it takes to complete one cycle or revolution. So basically, this works a lot like the T that you had before, the capital T, where this is the time it takes you to do one whole cycle. So like one whole oscillation, basically. Your frequency is measured in hertz, and that's 1 over T. So whereas T is the time it takes for you to do one thing, frequency is the amount of time, or the amount of things you can do in 1 second, basically. So they're inverses. Your omega is also equal to 2 pi times frequency, or 2 pi over T. And these problems are a lot of relating different equations together. So here is our practice problem. Oh, no, I want to do that. I didn't read it yet. Got too excited. Oh God, what's it doing? Oh my God. That's not good. All right. So we have a vertical spring with a spring constant of 450 Newton meters is mounted on the floor. From directly above the spring, which is unstrained, a 0.3 kilogram block is dropped from rest. It collides with and sticks to the spring, which is compressed by 2.5 centimeters, and bringing the block to a momentary halt. Assuming air resistance is negligible, from what height in centimeters above the compressed spring was the block dropped? we want to know how high above the spring we dropped this thing. Right? Oh, that's too far. Okay.
So basically what's happening is we have this object, right, which is above an unstrained spring. It's something. Then we drop it on top of the spring, and it compresses by 2.5 centimeters. And it also brings the spring to rest.
And we know our V final is also 0. So if we look at the kind of forces that are doing work here, we have springs and we have gravity bringing this thing down. So those are both conservative forces. Therefore, our work due to non-conservatives is 0. Our energy initial and our energy final will be the same.
This brings me to your completed energy equation.
So all the types of energy you know are linear kinetic energy, or mechanical kinetic energy, rotational kinetic energy, gravitational potential energy, and now we add in springs, spring potential or elastic potential energy, which is 1/2 kx. And that's it. That's all the energies you know. Congratulations, you have finished the equation until physics 2. So if we look at this, there isn't any mechanical kinetic energy because we start at velocity equals 0 and we end at velocity equals 0, right? So we don't really have to worry about that. We're not rotating, so that's another thing we don't got to worry about here.
We are changing heights, so we will need this, and we do have springs, so we will need that, right? So let's actually set up our energy initial equals our energy final.
So for initial, we have mgh initial plus 1/2 k x initial squared equals mgh final plus 1/2 k x final squared. So what we're kind of do is, well, first of all, our string starts unstrained, right? It starts unstretched, uncompressed.
So this x initial will be 0.
So that's pretty nice.
We're going to want to find our change in height, right? But so like if this is our equilibrium position here, we want this height here. But if we said that our h final was 0, then we would say that this 2.5 centimeters was also included in that. So you can do that and subtract 2.5 centimeters away from your final answer.
And actually, yeah, that's easier. So we're going to do that.
So we're also going to say that our h final is 0. Just remember that 2.5 centimeters is not included in that h initial, so you're going to have to do a little bit of math afterwards. So we know the mass of our object is 0.3. We know gravity, 9.8. We're trying to find our h initial, and that should be equal to 1/2 our spring constant k times our x, which is 0.025 squared.
So when you solve this out for your h initial, you should get 3.7 or 7.3, I'm sorry. Something like that. Centimeters, actually. You should
Ended up getting a 0.073 meters in the number. So then if you wanted the distance,
above where it was dropped. So what we calculated was this whole distance here. So in order to get just this distance, you have to subtract 2.5.
so our actual h should be 0.048 meters
All right, so we are basically done with this. I'm going to open up for questions too for another couple of minutes. So for some final tips, don't get overwhelmed. It's very easy to like see a wall of text and be like, oh God, I will never be able to decipher what this wants from me. You totally can, just break it into small pieces. You know like the smaller bits of a problem, so just break it into those chunks and it seems a lot more manageable when you do. For concepts, if you have trouble with concept questions where it's like, oh, if you halved the acceleration, what would happen? I like to make up arbitrary numbers and plug them into equations. It works. Physics takes lots of practice. I know a lot of you don't have your exams until like the last couple of days. You have lots of time to practice. I know you probably have other exams, but this one's really good. This is important. No. So just keep practicing and you'll get a lot better at it. Things can be done in a lot of different ways too. So don't think there's just one right way to do it. There could be multiple. And you're all going to do super good. I know you are. I believe in all of you.
All right. So
Does anyone have, also, when you leave, be sure to leave the room cleaner than you found it. Also, where'd the thing go? We have a fun
survey you can take.
maybe, hold on. Yeah. Nope, that's in. We have this QR code that you can take a survey. You don't gotta, it helps us. And yeah, so are there any final questions that everyone wants to do? Yeah. Yeah, so basically when you had your big equations where it was like a omega sine omega t and like a omega squared cosine omega t. So basically, if your sine is at maximum, if your sine equals 1, cosine is 0, right? So you can also see it like when you have a spring.